Ladies and gentlemen, as head of the Department of Applied Mathematics and Theoretical Physics, DAMTP, I'd like to welcome you here today for the second Andrew Chamblin Memorial Lecture. We're very pleased that Professor Sir Roger Penrose of the University of Oxford has agreed to give today's lecture. Before introducing Roger Penrose, I'd like to just say a few words about Andrew Chamblin, in whose memory this lecture series has been established. Andrew was born in Lubbock, Texas, and he attended Rice University, where he majored in mathematics. After graduating, he came to the UK, and he spent the year 1991-92 in Oxford at Christ Church, where he studied twistor theory and global methods in general relativity with Roger Penrose, who's our lecturer today. And then he decided to come to Cambridge as a PhD student to work in DAMTP. He was a PhD student of St John's College, and he worked under the joint supervision of my colleagues Gary Gibbons and Stephen Hawking. And this is a nice picture of theoretical physicists in action, with Gary Gibbons on the left, and then Andrew sitting next to him in the dark glasses, and Stephen unmistakably at the end of the table. So during his time in Cambridge, Andrew's interest turned to quantum gravity and to the newly emerging M theory. And over his subsequent career, he made a number of striking research contributions. He published about 50 papers, and he gave many talks and lectures around the world. After he'd completed his PhD in DAMT, he became a Draper's Research Fellow at Pembroke College, and then he moved on to posts and fellowships at Santa Barbara, MIT, Los Alamos, Queen Mary College. And then ultimately, he was appointed as an assistant professor at the University of Louisville in Kentucky. And it was sadly in Louisville that he died unexpectedly on the 6th of February 2006 at the age of 36. So Andrew's many friends and collaborators in DAMT and elsewhere were sad to hear of his death. And we in DAMT we greeted very warmly the idea that a fund might be set up to support a series of lectures that would perpetuate his memory and promote the broad area of science in which he was interested. And Andrew's family and Dr. Joe Ashbourne have been the prime movers in the establishment of this fund. The donations to the fund have come from Andrew's family and personal friends, from many members of the international theoretical physics community. And in fact, we now have sufficient money in the fund to allow an annual Andrew Chamblin Memorial Lecture in perpetuity. And it's a pleasure to welcome today many of those who've helped with this establishment of this fund, and particularly Andrew's mother, Caroline, and brother, Jonathan. Andrew's parents have also commissioned a striking bust of Andrew, which we have on display in DAMT. So each year, this lecture will serve as a chance to remember Andrew as a theoretical physicist who achieved a great deal in his short career, as an accomplished musician, keen sportsman, and for many, as a missed colleague and friend. So now I'd like to move on to introducing our lecturer today, Professor Sir Roger Penrose, who's well known for his distinguished work in mathematics and theoretical physics. Roger was himself a PhD student at St John's, as was Andrew Chamblin, and then a research fellow at the same college. He later became Professor of Applied Mathematics at Birkbeck, and then Rouse Ball Professor of Mathematics at the University of Oxford. He's received many honours and prizes, notably the Eddington Medal of the Royal Astronomical Society, which he famously shared with Stephen Hawking in 1975, a knighthood in 1994, and he was appointed to the Order of Merit in 2000. He's known not only for his work in mathematics and theoretical physics. For example, he invented twistor theory, he discovered Penrose tilings, and he, of course, did important work on singularities and general relativity, but also for his writing aimed at wider audiences, for example, on the connection between fundamental physics and human consciousness. So Roger's title today is Deep Questions of Cosmology, Did Something Happen Before the Big Bang? And so please will you join me in welcoming Roger Penrose as the second Andrew Chamblin Memorial Lecturer.
Well, thank you very much. It's certainly a very great pleasure and an honor for me to be able to give the second of these Chamblin lectures here. I supervised Andrew for a few months in Oxford before he came here. I can certainly remember him for the excitement and enthusiasm he had for his subject and his ability to recognize a good idea and run with it when he needed to. So it was, and he came here to a better place or whatever, and he clearly did great things when he got here, and it's very, very sad that he was taken from us in the prime of life. It's very unfair as well. So I'm glad to be able to give these lectures in his honor. So let's start with a question here. If I can turn this machine on. Here we are. Was there something before the Big Bang? This is a question which, had I been asked about 3 years ago, I would have said it's a ridiculous question. The Big Bang was a singularity in space and time, and so to say before was a meaningless question. But then certain ideas came to me which led me to change my view on this question, and I'll come to that. Perhaps I can leave this on the subsidiary screen. Now, there is a question, another question here. Is the idea crazy? To which the answer is clearly yes. But, well, you see, there are a lot of funny things about the universe, funny things about the Big Bang, and it's not just us that's crazy. It may be the universe, too. There are a lot of strange things. The one that I want to address most completely, perhaps, is the second law of thermodynamics. And the second law of thermodynamics is given to us in a particular way, which has to do with gravitational degrees of freedom being suppressed. I'll come to explain a bit more of that in a moment. But that's one topic that the idea will have something to say about. That's perhaps one of the most important ones. The issue of a cosmological constant, or dark energy, which is a great puzzle to people. I should say that it's absolutely crucial for the scheme that I want to describe that there is one. So whether it explains anything is another matter, but it has to be there for this particular scheme. Then there's the question of the other dark thing, matter. There's a lot of material in the universe that nobody knows what it is. Well, it has something to say about that, so let's come to that later. And there's all sorts of funny things about the cosmic microwave background, this radiation which seems to be coming to us, often referred to as the flash of the Big Bang, despite the fact it's what you're looking at is about 300,000 years after the Big Bang, but perhaps that's more or less the Big Bang. And it has all sorts of curious features, like, in particular, acausal correlations. I'll come to that. The usual explanation involves something called inflation. There won't be any inflation in this lecture, so if you're a fan of this idea, I suppose you can turn off at this point. It will have something, certainly, to say about the black hole evaporation information loss paradox, as it's called. Stephen Hawking was basically something which came out of his work. And there's something which, whether it's true or not, it seems to be important to this scheme, whether there's a slow decay of mass. I'll say something about all these matters. I won't say the scheme answers all the questions, but at least they have great relevance to what I want to say. So I'll leave these up here so you can still stare at them if you want to. Certainly the crazy has to be up there still. First of all, let me say something about the original models of cosmology according to Einstein's general theory of relativity, put forward by Friedman in 1922. And basically, there are these three models. There's a thing called lambda, that's this cosmological constant, or the dark energy, which I'll come to later. But these are ones where it's not present. And these are the standard cosmologies. Of course, here you have a beginning of the universe, which is the Big Bang. And I want to say something about these three different models in a moment. But before going on to that, let me say something about the one in the corner up here, the closed one, where there's not just a Big Bang, but also a big crunch. And I suppose one of the earliest before the Big Bang theories was the Friedman model itself, which I suppose because if you plot the radius of the universe against time, and I've done it here, it's what's called a cycloid, which is the curve you get when you roll a circle on a line, and it's traced out by a point on the circumference. And this thing keeps on going, you see, it repeats itself. So if you put down the solution to that equation, namely this repeating cycloid, you get not just one universe, but the thing keeping on repeating itself, you see. So for each one of these big bangs, there was a before, namely another cycle like this. So this sort of idea was already present in the earliest cosmologies. Tolman, in particular, worried about the second law of thermodynamics. If it repeats, you see the second law of thermodynamics says there's a thing called entropy, which is supposed to be increasing. And if it's increasing, how can it be keeping on going up without leaving its mark on the universe? So he suggested a model which, if I think I've got it the right way around, these cycles got bigger and bigger as time went on. It's a very particular model he introduced, and it only addresses a very tiny part of the second law. I'll have to say something a lot more to do with this second law in earnest. Wheeler had the interesting idea that the constants of nature might somehow get reset each time the universe went through one of these phases, because there are puzzles about the constants of nature seeming to have values which are just right for life to exist, and so it seems to be rather surprising that they have the right sorts of values. And so one suggestion is you might have lots of universes, and perhaps there are things like this, and we happen to live in the one where these constants have the right values. So that's at least the thought, which needs to be taken seriously, perhaps. Lee Smolin had an idea where the black holes, they have their own singularities, and those would somehow be sources of new universes. And then there are other ideas due to Veneziano and Steinhardt and Turok, which do involve some sort of concept a bit like this. These all involve higher dimensional string theory. Some of you will be pleased, and some of you won't, to hear that my ideas that I'm going to describe don't involve any string theory. So you can again turn off at that point if you want to hear about these kinds of ideas, but I'm afraid that's not going to be involved in what I want to say. I have trouble, particularly with this scheme, which is that the geometry, you have trouble fitting it. It also applies to other schemes when you consider universes with lots of irregularities. So we do have to worry about geometry, and that's something that I tend to worry about a lot. So I'll come to that again later on too. Let me, first of all, just say what distinguishes, apart from the temporal behavior, which is certainly different in this case, the closed case, from the other two. See, here you have a crunch where the universe comes together again. The others keep on expanding, although the one with k equals 0, the k refers to the curvature of the spatial section. So time is going up. So when you chop through this way, you see what space is like at any one moment. And the spatial sections for these three standard geometries can be best, I think, understood in terms of these pictures that, due to Escher, they're very beautiful pictures. Here we have tessellations of angels and devils, and here we have a Euclidean plane one. You have to imagine, of course, it's not a plane, you have another dimension, but that sort of thing you have to get used to. So you have the angels and devils repeating indefinitely and indicating that you have a flat Euclidean plane. There's also a model that Escher made. This is made of wood, and it represents a closed-up universe with positive curvature, and that's, again, angels and devils, but fitting together to form a sphere. This one here is the one I want to talk about mainly, not because I believe the universe has negative curvature spatially, which it may have. The observations are that it's very close to being the flat case. In a certain sense, that's the worst possibility, because it means we still don't know which it is. It could just be one way or just the other way. And if it was clearly one way or the other for one of these two models, at least we'd be able to say the evidence points to this or that. But if it's flat, it still could be one way or the other. That won't play much of a role in what I want to say, but I do want to say something about this particular picture. In fact, here's a bigger version of the same thing. So I'll put the other one here. And what I want to say about it is, well, first of all, it's what's called a conformal representation of what's called the hyperbolic plane. The hyperbolic plane is an alternative to Euclidean geometry in which you have parallel lines, more than one parallel through a point not on that line. I don't want to talk about that aspect of it. What I do want to talk about is, well, first of all, in this representation of the complete hyperbolic plane, we have what's called a conformal representation. It's often referred to as the Poincaré disk, I suppose because it was originally due to Beltrami. But this is the sort of thing you get in mathematics that names don't always actually... Well, Poincaré did rediscover it, whereas often the idea is given to somebody who didn't even know the results. So that's... never mind about that one. Here we have... what I want to point out is, first of all, it's a conformal. That is, that if you take small enough shapes, they will be correctly represented in the Euclidean background. Of course, the sizes won't be, because these devils look as though they're getting smaller and smaller, whereas if you happen to be one of the devils, or if you prefer an angel, you would think the universe was the same no matter how close you are in this picture. So you have to imagine there's a bit of distortion, but the distortion is of a nature that it doesn't alter the shapes if they're small shapes. So although the devils get a little bit distorted, if you take a very, very tiny shape, like the eye of the devil, you would find that the eye is more or less simply magnified or shrunk down, and it's this right shape wherever you are. And that's what's meant by conformal representation. So as you get very near the edge here, according to the devils or the angels, they still think this universe is keeping on going just as it would be in the middle. It's completely indistinguishable as far as their geometry is concerned. The point I want to make, though, is that the entire universe, right the way out to infinity in this hyperbolic plane, is represented in this finite region. So we, from our Euclidean perspective, can look down on this picture, and if we imagine taking a walk over the picture, we could take with one step, put one foot here and the other foot there, and we're beyond infinity as far as the angels and devils are concerned. So we have here a space with infinity represented as a nice, smooth boundary. And you could imagine that the universe would continue if the geometry was something which didn't respect size. If it just respected angles, then the geometry could be continued. But if you're worrying about the sizes of things, this really is infinity, and that's the end of it. Now, keep that in mind, because this will play an important role in what I want to say later on. Okay. Now, I want to say something about the second law of thermodynamics. In fact, the mystery of the second law of thermodynamics. You might say, why am I calling it a mystery? Because in a certain sense, the second law of thermodynamics is about the most natural thing you could imagine, because it's telling you that things are getting worse and worse, if you like. And we all know that, don't we? Things are getting more and more random in a certain sense. Well, let me be a little bit more precise about that. So I'll leave this one over here, just so you're reminded what I'm going to talk about. And here I have a cartoon of something. You can imagine as this is something going on according to Newtonian mechanics. You don't have to worry about relativity or quantum mechanics, although the arguments would apply just as well there. Well, quantum mechanics is an issue, but don't worry about it here. This is, say, a Newtonian picture, and here we have some process going on which is completely consistent with the dynamics according to Newton. Here we have a glass of wine perched on the edge of the table. Something jiggles it, it falls off, the wine splashes out, and the glass smashes, and the wine gets absorbed into the carpet. Now, the thing is that everything that's going on in the dynamics here is completely reversible in time. Newton's laws are completely reversible in time, so it would be just as consistent to start here and then there and then there. But you never see that happening. So one way of sort of explaining, or that's perhaps the wrong word, one way of describing what is going on, which says the evolution should be in this direction, is to say that this thing called entropy, which roughly speaking is a measure of disorder, is increasing in the direction in which time increases. And that is the second law of thermodynamics. Well, that's a little bit vague, you might say. What does disorder mean? Well, it's very nice that Boltzmann produced a beautiful formula, which is, well, it's such a simple formula, you can just write it there, you see. It's on his gravestone. It's not so easy to find a formula that you can fit on a gravestone nicely. I don't think that was why he used it. But S here is the entropy. the logarithm, well, you're supposed to know what a log is for this. The k thing here is the only thing which isn't due to Boltzmann. It's called Boltzmann's constant. But he knew what he was talking about, even though he never worried about the actual values of things like that. The volume here, well, what's that? That's a volume in something, not ordinary space, but something called phase space. Now, what's phase space? Well, you have to think of this picture, or all these pictures, made up of lots and lots of particles, and each particle has a position that would require 3 numbers, 3 coordinates to specify it, and each particle will also have a motion, a velocity, let's say the momentum, which is more correct technically, and that's 3 more numbers. So 6 numbers to describe each particle, or at least how it's behaving, a few more like its mass and things like that. But let's just think about its motion and so on. Then each particle, and suppose there are a zillion particles, then you have 6 zillion numbers in order to characterize the state of what's going on here. So this space here, phase space as it's called, is supposed to be a space of 6 zillion dimensions, where the zillion refers to the number of particles here, 6 zillion dimensions, and the evolution of the system, according to Newtonian dynamics, would be described by some curve wiggling around in this space. So that's how we like to think about it. And, well, what does this V? Well, what are these little compartments here? They're what are called coarse graining boxes or compartments. And what they mean is that if you take 2 points in the same one of these bubbles here, they describe situations which look the same. Now, that's a bit vague. But putting it another way, you say that there might be macroscopic parameters such as think about the air here. You see that the gas would have a certain temperature, a certain pressure, a certain motion. It would be moving somewhere or another. And there would be a certain number of parameters which would pretty well describe all you need to know about the gas. And there would be lots of different ways that the individual particles could make up that gas in accordance with those macroscopic parameters. And the thing is, we lump them all together in one of these compartments. Okay? Now, the volume, it's a big high-dimension volume, but it's still a volume in the usual sort of ordinary sense. That volume is V. You take the logarithm of it, time is constant, and that's the entropy. So it's really quite as simple. In some respects, it's a much simpler notion than many other things that you have to consider in physics. Now, I want to make one point here, which is very important for understanding what's going on. That is that these volumes, unlike this picture, because I've tried to draw this in 2 dimensions rather than in 6 zillion dimensions, these volumes tend to differ absolutely stupendously in size. So this next one here, compared with the one which is going to start, that point here, say, represents the glass of wine on here, the next volume is likely to be absolutely stupendously larger than that one. So if it finds its way into another volume, it's likely to be much larger by a huge probability. And the chance of finding the smaller one again is almost 0. So it's sort of misleading when you look at this formula. And it's also because k is a small number, and particularly because logarithm tends to make sort of tone down differences in size by an enormous amount. So the entropy difference between this volume and this volume might not be very much, but if it's anything sort of measurable at all, that will correspond to an absolutely stupendous difference in the size of this from this one. So this means then that as this point wiggles around, it's likely to find itself into huger and huger volumes, and the chance of getting back into a small one you can more or less ignore. So that's the second law. We've more or less understood it, and the entropy is going to go up because you're going to wiggle around and find larger volumes. The only trouble with this, it gives us a nice prediction, you see. If that's now, then the predicted entropy is going up. But there's something fishy here, because the Newtonian laws are symmetrical in time. So where's the asymmetry in time come from? Well, you see, I'll put this another way. The question we've been asking is, if the glass was perched on the edge of the table, what's likely to happen to it? Well, this and then this. But let me ask you a different question. If the glass is to be found perched on the edge of the table, what is the most likely way for it to have found itself perched on the edge of the table? Well, we look at this argument again, and you see what's the most probable, a lot of the main ones of these paths which get into that region we're concerned with, well, almost all of those paths start from bigger and bigger volumes, and they tell you that the entropy indeed should go up in the past as well. Or putting this in sort of ordinary terms here, what's the most likely way that the glass found its way in the corner of the table? The most likely way, according to this argument, is it started off a mess on the ground like this with all the wine spilt into the carpet. Suddenly the glass assembled itself, and the wine all jumped back into the glass and sat itself on the corner of the table. Of course, that's wrong. The right answer is that somebody who'd evidently been drinking a little bit too much of this stuff had perched this glass on the edge of the table and wasn't quite careful what had happened, and it fell down. Well, that's something consistent with the second law. It's this curve here, not that one. So the argument works in the future, but it simply gives you an absurdity. It gives you completely the wrong answer in the past. And that's because the argument is only any good if that's all there is. Maybe there's some reason, quite apart from this argument, which is telling you why the entropy had to come down in the past. In other words, if I look back into the past, I find that this curve keeps on going down and down. That's what the second law is telling us, until you get to the Big Bang. And that was supposed to be the beginning, and so it must have been very tiny. Okay, well, that's reasonable. There must be something very special about the Big Bang. Well, how do we know there was a Big Bang anyway? This is, I'm going to put this over here, I think, for the moment. How do we know that there was a Big Bang? Well, one of the best pieces of evidence for the Big Bang, I did say, that was this microwave radiation, which I referred to a moment ago, which is often referred to as the flash of the Big Bang. And it's such an important observation that it got the Nobel Prize on two completely separate occasions. Well, it's important anyway, apart from the Nobel Prize. And I want to show you this curve here. This curve, this way we have the frequency of the radiation, and this way we have the intensity of the radiation. And these little lines represent the observational error bars. The curve itself is the famous Planck curve, and this is a fantastic agreement with that. It's a lot better than it looks at first sight, because these error bars are multiplied by a factor of 500. And this means that really the error bar is only a 500. So even if you take the worst one, the end here, you divide it up into 500, it's going to hug that point. So you have to think of all the observational points are absolutely spot on the curve. Now, what is that telling us? What is the Planck curve, after all? What's it supposed to be? Well, it's what you get when you have particles and radiation in equilibrium, in thermal equilibrium. Now, what is thermal equilibrium? Well, I didn't actually mention this before, although it was clearly marked on the slide. Thermal equilibrium is the largest, corresponds to the largest volume, coarse graining volume in the whole picture. It's so big, it tends to be much bigger than the rest of them all put together. It's absolutely huge, and it's where everything ends up if you leave it long enough, so to speak. So it's the maximum entropy state. Maximum. So that means that as you trace your way back into the past, you end up, as it goes down and down into the past, it ends up at a maximum. Well, that's supposed to strike you as a little odd, because, after all, maximum is the biggest, not the smallest. So what's wrong here? Well, I think a lot of people tend not to worry about it as much as they should have done, because, well, after all, the Big Bang corresponds to a very tiny universe. And you might say, well, the universe was very small in those days, so maybe there wasn't much room for much entropy, or something like that. And I have a feeling that that's why people didn't much worry about it. But that argument is wrong, I have to say, because if you're considering dynamics, which includes the geometry of the universe as part of the dynamics, according to Einstein, that dynamics, as you trace it backwards or forwards, doesn't lose any degrees of freedom. The phase space is just as big as it was at any stage. So the entropy, if it was a maximum in the early stages, that should have been big here. There's no reason why, there's no constraint on the degrees of freedom just because the universe was small. There's just more complicated geometry and so on. The thing is that there is some other reason why it was special. And what you're looking at in this radiation is, as I just said, matter and radiation in equilibrium. That's what you're looking back at. And matter and radiation in equilibrium is not the whole story. It's very much not the whole story because it ignores gravity. I should say that this radiation is not only hugs that curve very closely, but it also is very uniform over the sky. And that uniformity is an indication that the universe was, in fact, very regular in early stages. And regular, perhaps I'll put this Planck curve back over here. Regular, well, in a gravitational context, here's another sort of cartoon like this. Let's consider the top pictures here. This is the situation of a gas in a box, which you might imagine it starts off in the corner here, and you then remove, say, compartments that were holding it in the corner, and it spreads out over the box. So that you see that the uniform, this is just sort of in rough terms, the uniform-looking picture corresponds to high entropy, and the thing being all tucked up in one corner corresponds to low entropy. Now, that's fine for a gas, but suppose these were gravitating bodies. I mean, maybe these were stars roaming around, if you like. Then there's an opposite tendency for them to clump, basically because the gravity is a universally attractive force, and so the clumped states are to be regarded as larger entropy than the uniform ones. So you have these two opposing tendencies going on at once. And what we find in the Big Bang, or close to it if you like, is a combination of this and this. So it's those two is what we find. And this is not maximum entropy, because as far as gravity is concerned, it's a very small entropy. So just to carry that argument a bit further, let me consider, in fact, why are we here? Well, lots of reasons why we're here, but one reason is that we're alive, and that's because of the sun. And that's because, well, people might say we get energy from the sun. That's a bit misleading, because the sun does, in fact, give us energy, but all this energy goes back again into space, particularly at night, you see. And if it didn't go back into space, the Earth would just get hotter and hotter. Of course, it is because of global warming, but that's a relatively small effect on this scale. It's not something that we should consider as unimportant, but nevertheless, for this part of the argument, it's not going to be a big effect. The main thing is that the energy does come in and go out. The main thing is that not just that the sun is there and hot, but the sun is a small hot spot in an otherwise dark sky. And well, it's hotter than the background sky, and since it's hotter, again, because of Planck, you have the fact that the frequency of the radiation is higher on average than what you get going back into space, and since the frequency is higher, the energy is higher, and since the energy is higher per photon, that means the same energy coming in as going out has to be shared out among a smaller number of photons coming in and far more going out. So that means that you have many, many more degrees of freedom going out than coming in, and therefore much larger entropy. So the whole point is not that we're getting energy from the sun, but we're getting our energy in a low entropy form. Schrödinger made a big point of this in his famous book, What is Life? And I think a lot of people sort of failed to appreciate the point he was trying to make. So what the point is about the sun is that it helps us to keep the entropy down, and it's the plants that do it for us by photosynthesis. They use the high-energy photons, spew them out as low-energy photons, many more photons, and it uses the low entropy in this smaller number of photons to build up their substance. And then animals eat plants, and we eat animals and plants, and so on. And that's how we manage to keep ourselves going. Okay, now the key to this is that the sun is there. It's a hot spot in a dark sky. Well, the sun, of course, involves in all sorts of processes, thermonuclear reactions, and goodness knows what. But the key thing is that it's there at all. And it's there at all because of gravity. all these other things, if you like, are additional things. In fact, without the thermonuclear actions, the sun would actually be hotter. It wouldn't last as long, but it would shrink down and become a very hot spot for a short while in the otherwise background sky. So the point really, ultimately, is gravity, and it's because of gravitational clumping. So it's the same thing as we had over here. The sun is an example of something where you have this clumping, and it's taking advantage of the fact that we had a uniform previous distribution that caused, when it condensed, it produced the entropy, which was low because the gravity was the gravitational potential for entropy was not being used for a while, and then the clumping caused it to produce a manifest temperature imbalance. Anyway, that's more or less the story. Okay, now I want to improve on these pictures a bit here. You see, these are completely uniform, these models, for reasonable enough reasons. If Friedman was going to solve his equations, he didn't want a great mess of irregularities here, so he assumed that the universe was very regular. And otherwise, we have to take into account that there will be very great clumping, and you have, in fact, black holes as the sort of maximum entropy state produced by this clumping. And black holes have their own singularities. I'll come back to that in a moment, but I want to draw them on the picture. So I'm going to amend this picture by putting the black hole singularities on too. So that's a bit of a better picture than we had before. But I want to improve that picture now in another way, because this picture, remember, that was the Friedman situations with a zero cosmological constant, but since 1998 or so, and later, the evidence has been piling up that there is probably something, a cosmological constant or something equivalent to it, which is positive. And that means that these models, whereas they used to look like that, and perhaps I should keep reminding you what the old ones looked like. They used to look like that. They all look pretty much the same, which in certain respects is rather boring because it means the future behavior is pretty well the same, whichever of these models it is, and the universe accelerates in expansion in later stages. So that seems to be what we're presented with. Lots of people don't like that very much because it seems to, they say, what on earth is this cosmological constant doing there, or this dark energy doing there, when we had no reason to believe in it for other. In fact, it's said that Einstein called this his greatest blunder. Turns out not to be a blunder at all. It was one of his greatest achievements, but he thought it was his blunder. The blunder was that he introduced it for the wrong reason. But it turns out that it's probably true. Okay, so I need it for what I'm going to say. So although I resisted the idea for a few years, I have to say, I've come round to it, and I think it's probably is really true that there is a cosmological constant. Well, I have to improve the picture yet more by putting in the black hole singularities too. So this is the sort of picture that we must come to terms with in the universe as we seem to know it now. Well, what's happened to the second law of thermodynamics? Well, you see, you have singularities in the past and in the future, because these black hole singularities are sort of future singularities. But in fact, they're of a very different kind, and I want to try and indicate that here. I'm going to introduce something called the Weyl curvature, and I want to try and explain what that is shortly, but just take it on trust for the moment. There is something, a kind of curvature of space-time, which is called the Weyl curvature. And this seems to be pretty well zero at the beginning, just observationally, and it seems to be very, very high in black hole singularities. That's more a theoretical conclusion. So we have huge Weyl curvature in the black hole singularities and tiny one in the initial state. In fact, eliminating this Weyl curvature in the beginning, however that was done, required the universe to be special to an extraordinary degree. We're talking about these phase space volumes, if you like. So if we go back to the phase space volumes that we had in this earlier picture, it's a question of how small was that phase space volume corresponding to the Big Bang? Well, it's got to be a ridiculously tiny point, and for reasons which come from Stephen Hawking's and Bekenstein's arguments about entropy of black holes, we see it's something like a precision of 1 part in 10 to the power 123. Well, that's using baryon matter. If you bring in the dark matter, it's at least a 4 up there. Not going to make much difference. Actually, it's an absolutely stupendous difference, but it doesn't make any difference to the argument. So we're looking at some incredible precision in this Big Bang, and that incredible precision, well, let me try and say something about that number. You see, suppose you take the, I suppose I just write this out as 1, 0, 0, 0, 0, 0, 0, 0, and I try to put a 0 on every proton in the observable universe. That wouldn't be nearly enough. So it's pretty big. Okay. I should say something a bit more about black holes now. In fact, here we have a space-time diagram of collapse to a black hole. You notice it's got these funny little cones all over it. Well, I should say explain about light cones. That's very important. So let me start by explaining about light cones. They have an important role to play in what I want to say. Here's a light cone. You must think of that as a space-time diagram. I've got 1 time dimension and 3 space dimensions. You can't see all of them, but forget about that. And that's the cone. And to think what that cone is doing, I just imagine time evolving. And it's, you see, this intersects in a sphere. Okay, it doesn't look like a sphere. It might look like a circle to you. You've got to have another dimension. So think of it as a sphere. It shrinks to nothing, and then it expands out. So that picture represents an evolution which is described by this, which I can show you with another picture here. Okay? Now, that's the light cone. This is the spatial representation of this. My slicing is going up like this, and there is the flash there. This is how light behaves. So it starts as a flash there. The next moment it's up there. The next moment it's there. And these represent these different sections, expanding out with the speed of light. There's a pass cone, too. That's got the minus sign on it. It's the pass cone. That's a sort of light sphere coming down, collapsing on that point all simultaneously. Now, special relativity, you have to imagine all these cones being plastered all over the space-time, as I've done it here. Photons will be represented by world lines. You see, a world line is the history of that photon going along. Always that world line will be tangent to the light cones. A massive particle, since it's supposed to be slower than light, will be represented by a world line which is within the cones. General relativity, these cones are just wiggly and all over the place. So that's the basic difference between special and general relativity. I suppose I should explain this black hole picture now. You see, it's a good example of this thing here, where the cones are not sitting nice and upright. They're sort of all over the place. And the point is that they tend to get tilted over. But, see, here's some collapsing mass. That's some body, maybe a star or something. As time progresses, you think of that body collapsing. It reaches somewhere where the light somehow can't escape, so that the cones you have to think of as being tilted over. If you're within this surface here called the horizon, they aim you towards that horrible singularity in the middle. If you're outside, there's still a chance you can escape to the outside world. So that's a picture of a black hole. Now, I want to try and describe to you what the Weyl curvature is. That's what I was trying to do here. So let me try and do that. In fact, those of you who know about relative differential geometry and all that stuff, I can put this slide on the side here. So the Weyl curvature is here, you see. It's that C thing. But I'm going to do, you don't have to worry about that if you're not familiar with these ideas, but I thought it's best to show the proper people what that thing looks like. So, okay. Now, one thing that general relativity tells us about light is that it bends. See, this little tube out there represents the history of a star, let's say the sun. That could be the sun here, and these are some distant stars. And the light gets bent so that two stars here, their light might get bent one side or the other. So when you look at the stars, because you see these rays continued as though the stars were a little further apart, it would look as though the stars are further apart than they actually are because of the presence of this internal body. Well, that was one of the big tests of general relativity. But here we have now, you suppose you're looking at the sun, and I'm going to imagine you could see right through it. So although the light doesn't get through. Let's just imagine the light rays would still get through. Now, the sun itself behaves like a lens, a positive lens. And that is an effect of part of the curvature called the Ricci curvature. So I put Ricci, R-I-C-C-I, that's Ricci curvature. And that is the magnifying effect due to the presence of the matter in the sun. And the Weyl curvature is a distorting effect due to the gravitational field. So as you look at the sun, if you like, you're not supposed to do it without your special glasses on, but forget about that. If you look at the sun, you will see that the field of vision gets spread out, that's this effect here, but also you get a distortion. That is, something which should have looked circular to you looks now elliptical, stretched out. Whereas as far as the Ricci tensor in the middle is concerned, it's just magnified. So that's a pretty accurate sort of picture of what's going on. Ricci is the magnifying effect, Weyl is the distorting effect. And okay, that's the difference between these things. That's more or less it. Has this behavior on light rays, but let's not too worry about it there. The thing about the Weyl curvature is that you can see it. Well, you see, here's a wonderful example. I hope you can see it. See, one of the troubles with galaxies, of course, is that they're already elliptical, they tend to be. So if you look at one, how do you know it's distorted? If you knew it was a completely spherical globular cluster or something, then okay, if it's distorted, then you could believe that's due to some lensing effect or something. But if you just look at a galaxy, how do you know? Well, of course, you've got to dig it out of the statistics. Well, you don't necessarily have to dig it out of the statistics because I've looked at this picture so many times now that I can't see it anymore. But I think you'll see there are these sort of ring-like aspect to it where you get stretching in that direction. In fact, with another picture here, it's much more obvious here. You can see these effects right the way around, which is telling you there is something, a great big mass in the middle, which, like my pictures, which I just showed you a minute ago, these pictures here, I hope you had enough of those formulae for the moment. Here we have that. It's just the same effect where if you could see the middle, yeah, there is a magnifying effect here, but you can't tell that because you can't tell what's being magnified, not because you certainly don't know how big it was at the back. But what you can tell is that there is just a sort of overall effect of distortion, which in this case you can spot pretty easily by eye, even though to do this properly you need to dig it out with a lot of statistics, just to show you that these effects can be pretty big. There is a distortion of some object which must have been pretty compact and roundish, stretched right out like this because of some massive object there. This is much further behind it, you see. That massive object is distorted, and because of the Weyl curvature, it has been distorted in this way. So you can see Weyl curvature. And, well, I was going to... I put my other slide somewhere. It doesn't matter too much, perhaps. For those of you who like the equations, I just want to say that the Weyl curvature is all this stuff, where the Ricci curvature plays the role of the source. That's like the matter in the sun there. And the Weyl curvature is the field. It's like in Maxwell theory, the Ricci curvature corresponds to the charge current vector. That's it. The charge current vector, and the Weyl curvature corresponds to the Maxwell tensor. Okay, if you don't know about these things, don't worry. But, okay. So, there's something else that I should say about the Weyl curvature. It's a measure of, it's about half the curvature. You see, in these pictures here, I showed you what's called a conformal distortion. That is, the devil's eyes are more or less the right shape. It's just that they are too small when they get to the edge, if you like. And that's something which is preserving the conformal structure. So conformal means you can stretch or squash as long as you do it uniformly. And the Weyl curvature, according to this picture at the bottom, I suppose I've called it, is actually a measure of the conformal curvature. So that's what it does. Well, what does conformal really mean in space-time terms? Well, I've drawn light cones for you, but the light cones don't tell you all the information. There's a bit more. Because the light cone, okay, it tells you how light behaves, but it doesn't tell you how clocks behave. So you have to imagine that this light cone, there are these surfaces there which tell you the first tick of a clock, if you like. So here's a clock whizzing along at great speed, and here is its first, there's its 0th tick, if you like, its first tick, its second tick, its third tick. Another clock, just the same kind of clock, so it ticks at the same rate, but because of the relativity effects, its first tick is there, and second tick and third tick, and so on. So you have to draw wherever the world line of that clock is, and you see where it intersects these surfaces gives you the succession of ticks. So these surfaces here are what you have to add to the light cones to get the full metric. Now, the full metric, it's usually written with a G or GAB or GIJ or G mu nu or something like that. The G doesn't seem to change much, but the other letters can do that. It's got what's called 10 components. So you see, you need 10 numbers at each point to tell you what that metric is. Now, 9 of them are telling you where the light cone is, and that's the conformal geometry. 1 is telling you the crowding of these surfaces. So the conformal geometry, which is the 9 components here, telling you where the light cones are, is almost the whole story. There's just a little bit more, which is telling you the crowdedness of these equal time surfaces. And that is, well, I can improve one of my earlier pictures. Let's put my thing up there so you can keep staring at it. And remember, this picture I had to describe light cones. I want to improve them that picture now by putting in these equal time surfaces here. So that's the conformal geometry. That is the full metric geometry. Each point, we've got 9 numbers to characterize where the light cones are. This one gives you the 10th component. So now you understand conformal geometry in relativity theory. Okay, now I want to use this idea. Remember I said that what seems to be special about the Big Bang is that the Weyl curvature, which is a measure of the sort of conformal part of the curvature, the more primitive type of curvature, the Weyl curvature apparently was 0 or pretty small in the early stages. Now that's a very nice condition, just as a hypothesis. You could say the Weyl curvature was 0, say, in the initial state. But it's a bit, the trouble with that is that there are all sorts of different versions of that. You can say it in one way or another. And because the Weyl tensor is a tensor and it's got lots of components, and to say what you mean by going to 0 is you get, since the Big Bang is a singularity, what does it mean to say it goes to 0 as a singularity? It's one of these tricky mathematical questions that can be very awkward. So I'm not going to do it that way. I'm going to do it another way, which has been particularly exploited by Paul Todd, and he's worked out in terms of another way of phrasing the Weyl curvature hypothesis, what the implications would be. So the Todd version is to say, okay, let's say, just like the picture that we've had here, pretty well like this, although now I'm talking about a singularity, I'm going to suppose that the Big Bang is a bit like this boundary here, and that it's really nice and smooth. If you could stretch it out, which is what I'm trying to do here, so that I stretch it out by leaving the light cones unchanged, but I change the crowding of those equal time surfaces. So the conformal geometry goes right down smoothly to this beginning. Another way of saying this is that, like in this Escher picture, you could step outside this. You see a Euclidean person could say, well, okay, I can just continue the geometry out here. That conformal geometry can be continued. So I'm going to say the same thing here. This hypothesis can be phrased now as by saying that the space-time as a conformal structure, as a light cone structure, if you like, can be extended to beyond here. Now, this is a mathematical trick. I want to get that clear. I'm not saying that there's something down there before the Big Bang. I'm saying that if you, just mathematically, it's a very nice trick mathematically to say, let's pretend that there's something down here, and then you can extend this universe to this prior stage, and that is a way of phrasing the condition very nicely mathematically. And that's a very beautiful way of doing it. Now, is it just mathematics? That's the next question. Well, there's a certain indication that there might be something a bit more physics about it than just mathematics. And that is, well, how do you measure this crowding of the surfaces? See, I just drew the picture here, and I have clocks, and they determine where those crowding surfaces are. But we can actually say something a bit more physical. What we can do is say, well, okay, suppose there weren't any clocks. And what is it that makes a clock? Well, the main thing about a clock is mass. And this comes from two very, very basic equations of physics. One due to Max Planck, that's the E equals h nu, which I referred to before in the photons from the sun. And the other is Einstein's even more famous E equals mc squared. So if you simply combine these two, eliminate the E between the two, you see that the frequency and the mass are directly proportional. Apart from these constants here, which are supposed to be just conversion numbers, they are more or less the same thing. So any particle has a natural frequency associated with it, and that's a clock. So particles are clocks. Of course, clocks are, if you want to make an actual clock, you have to have lots and lots of particles, but it actually comes down ultimately to the same thing. You're ultimately depending upon masses to determine your time scale. Now, when you get close to the Big Bang, energies get so high that the masses of particles become more or less irrelevant. So that, in effect, the physics going on near the Big Bang is more or less conformal physics. Now, that requires a little bit more than I just said, but a lot of, well, it really depends on the laws of particle physics, which aren't known accurately enough, but the sort of view that we have at the moment is that the laws right close to the Big Bang should have this invariance and behave as though they're massless and behave like, say, electromagnetic interactions, which don't seem to care about how massive things are. They're conformally invariant. So that means, as far as this is concerned, you don't seem to know. The physics of the Big Bang doesn't quite know where this surface is. It's not particularly interested in it. So as far as that physics is concerned, there might have been something going on before. So near the Big Bang, energies get so great that mass becomes irrelevant. Particles are effectively massless. Now, I want to say something about the other end of the world, the extremely remote future. Now, a lot of matter collapses into black holes. Eventually, the expanding universe cools to lower than the hole's Hawking temperatures. The larger the holes, the lower the temperature, and it's always very slow. And then the black holes disappear with a pop. This is what Stephen has told us, and I'm certainly going to rely on that here. So this is, but it's a controversial issue, and I want to illustrate that here. There's a thing called the information paradox, and I'll come back to this, but I should say there's a certain controversial aspect to this. But let's not worry about that for the moment. I just want to consider the fact that the black holes eventually will disappear with a pop. I say pop rather than bang because it's not all, okay, it would be a nasty thing in this room. It would probably kill most of us, but it's, from the astronomical point of view, it's a pretty trivial thing. But on the other hand, it takes an awful long time. For a black hole of the mass of the sun, it would take about 10 to the 64 years. That is 10, with the 64 zeros, one followed by 64 zeros. That's an awful long time when we consider it's only 10 with about 10 zeros that the universe has been around for. If it's a big galactic black hole, you see, our galaxy's got a big hole of 3 million solar masses, and other galaxies have even bigger holes in their black holes in their centers. They'll take a lot longer. So it might take something like 10 to the 90 years. It's an incredibly long length of time. And eventually they decay and disappear into radiation. But one of the things that's made me think about this sort of idea I want to describe is just how incredibly boring this universe seems to be. We're stuck with this universe. We seem about as boring as it could be. I mean, can you imagine anything more boring than waiting around for a black hole to go off pop? Seems to me to be just about the limit, And then the universe isn't much more interesting after that. I mean, probably even more boring. So it seemed to me we're stuck with this incredibly boring universe. But are we? You see, I'm not sure it's on this transparency here. But are we? Because, well, I'll come to that. I think I'll go to the next transparency here. Yes. you see, what's going to be left pretty well are going to be mainly photons and things like that, which don't have any mass. There are certain little problems about maybe the odd electron might be hanging around and spoiling things, which is why I want to have as a sort of hypothesis that maybe electrons and other massive things, the mass sort of fades away. And it's not so stupid when you come to think of the reason we think mass is a constant in ordinary physics, because we use a thing called the Poincare group to determine the mass, and we use things called the Casimir operators, which commute with everything else, and one of these determines the mass. And if that's not quite right, because we're using the wrong kind of asymptotic future, we're not using the kind of particle physics that seems to be usually used, because of this cosmological constant, maybe mass isn't quite a constant. That's an issue which certainly one would have to worry about in this whole scheme. But I'm not going to worry too much about it here. At least as far as most of the things in the universe are concerned, they would be massless. And let's say photons, which don't have any mass, and it's pretty hard to bore a photon, I'll tell you, because a photon doesn't experience the passage of time. So a photon simply, blip, and that's infinity as far as it's concerned, and it doesn't care too much about this time business. It's not interested in time. It just, this is really like this now, you see. This is infinity in the Escher picture, and now I'm talking about infinity, the temporal infinity, right in the remote future, and the photons are things which don't care about the metric. They just care about the conformal geometry. So infinity is no big deal as far as a photon is concerned. So, in fact, this is a trick that was used even before the Big Bang trick, just for studying the behavior of radiation out at infinity. And as a mathematical trick, you can say, well, let's suppose that you look at it from a conformal point of view, and then there's seems to be a nice smooth boundary which represents infinity, and you could imagine stepping outside to, if you're a conformal person, stepping outside to what's beyond. So we have two ways of continuing. We can continue through the Big Bang, and we can continue through infinity. And I put both ways on the same picture here. Here we have the universe drawn in sort of more usual way. We can stretch out the Big Bang to be a smooth boundary in the past. We can squash down infinity to produce a smooth boundary in the future. And both of these are mathematical tricks. But maybe it's not such much a trick, because after all, the things that are going on in the universe, there's a good reason to suggest they might be totally massless things which don't even care about the metric. So here is the crazy idea. Took me a long time to get there, but here it is. Crazy idea is that the present universe that we know about and describe is simply one, what I'm calling eon, of an endless repetition of these things. Now, when I say repetition, I don't mean that this is exactly the same as that. I don't even mean that it need be the same constants of nature. It's possible, in accordance with the, say, Wheeler type of idea, that these constants of nature might get changed from eon to the next. So this is a worrying thing. It would be much nicer, as far as working out the implications of the theory is concerned, if this physics was unchanged from eon to eon. And I think it's best to assume that to begin with, and if one runs into trouble with that, well, at least there's one place you can step and see whether that helps. Okay, so that is it. It's called conformal cyclic cosmology, and the idea is that the universe never recollapses. See, the key thing about this, it's not like the original Friedman cyclic universe. The universe never collapses. It just gets on expanding and expanding and expanding, but it gets to the point where it sort of forgets how big it is. The things in the universe have no way of keeping track of time, so a very big universe and a very small universe are equivalent. And that's the idea. It needs a little bit more than that, and you have to develop some equations to make sense of it, and indeed that's what one does, but I don't really want to go into that here, because this is more of a sort of popular lecture where I shouldn't draw too many equations. Okay, so that's the idea. Well, I've drawn it here in a different version here. Is this an idea which is just so ridiculous that we're never going to be able to test it? Well, it's not like that at all. In fact, it has very powerful tests that could be applied. And I want to consider the following, which seems to me be one of the major effects. This is the eon prior to us. This is our eon after this. This squashed down is our Big Bang. This stretched out is the infinity of the previous eon. Now here I've drawn the history of a few black holes coming together, maybe in galactic centers. Maybe you have in clusters of galaxies. The galaxies tend to run into each other from time to time. When they run into each other, then from time to time their black holes will run into each other. When they get close, they will emit large amounts of energy in the form of gravitational radiation, a very significant amount in comparison with the masses of the black holes already. So you have to bear in mind that quite a large proportion of the energy in black holes in galactic centers will come out ultimately in gravitational radiation. Now this gravitational radiation makes its way out to this boundary which joins the two eons together. And, well, this is a technical detail, but what you find is that the Weyl curvature does indeed go to 0, so the Weyl curvature is 0 on that crossover boundary. However, it doesn't go to 0 and sort of stay there. There is a rate at which it goes to 0, what we call the normal derivative of the Weyl curvature across this junction, and that normal derivative will affect the matter in the next eon. And there are certain aspects about exactly what, well, you have to worry about what that matter is. In fact, what has to be, in order for the equations to make sense, there has to be a whole lot of new matter created from one eon to the next, so that the Big Bang of the next eon contains a lot of matter which didn't simply come from the eon before. What is that matter? Well, the hypothesis is that it's dark matter. So that's, I mentioned dark matter, and does that have a role to play in this scheme? Well, it does seem to. That's, of course, goes beyond the conjecturing that that's dark matter is something which goes a little beyond the other assumptions that I'm making here, but at least it's a reasonable thing to expect. And the distribution of that dark matter will be influenced by these gravitational radiation bursts. The picture which is quite useful to think of here is ripples on a pond. Suppose you have a pond, it's raining, each drop produces a ripple going out, circular-looking ripple, and the next drop puts another one, and then perhaps the rain stops after a while, and then you look at it a little bit later than the rain after it stopped, and you see, well, just ripples. But if you were clever doing the analysis, you could work out whether that pattern of ripples was made up of individual points of rain. And that's the sort of thing you should be seeing as we look out to the sky. So the microwave background, the slight variations that we see in that microwave background on this scheme are caused by these black hole encounters, primarily by these black hole encounters in the previous eon. And it does mean that you ought to see something of patterns like this in the sky. Well, when I was in Princeton just about a month and a half ago, I made a point of talking to David Spergel, who is an expert at this sort of thing. And he told me, well, first of all, I said, well, why hasn't anybody seen these ripples? And the reassuring thing he told me, well, nobody's actually looked for them. So at least that's one step, you see. They might be there. And then he said, which was a bit more alarming, he said, well, it wouldn't be too difficult to find out if they're there or not. Well, I've been giving lectures a bit like this in other places, and I thought, whoops, that means I'm going to have to change my lecture. Well, I don't know. So, in fact, I've been talking to David Spergel and his student on email, and just before giving my lecture here, I went up to my room that I'd been assigned to me to see what. I told them I was going to give this talk, and please tell me what the situation is so I will know when I come here. Well, they sent me some long, complicated things and attachments and this and that, and I simply didn't have time to look at it. So I'm afraid I can't give you the answer, but I go back later and study it carefully. It seems to be one of these things you really have to look at it very. That was really what I was expecting. One of these things you have to look at very carefully to see whether it says one thing or the other, or does it say anything. So that is left in a rather tenterhooks situation, I'm afraid. I just want to finish with one other thing, which is to do with the key problem which I talked about, which is the second law of thermodynamics. See, there's a sort of puzzle going on here, because the photons, in a certain sense, go right through. Their degrees of freedom on one side are the same as on the other. Even the gravitons, they leave just as much mark on the other side as they left on the others. So there, in a certain sense, there's no loss of information. If there's no loss of information, how is it that the phase space suddenly gets shrunk down to what you expect for a very uniform universe in the next, it took me a lot of time to figure out what the theory is really telling us here. And it's absolutely crucial in this picture, and I'm afraid some people in the audience won't like this too much, but I can't help it. It's what I've always believed since Stephen, first of all, brought this up with me. It's this information paradox, so-called. What happens to the information in the sense of phase-space volume to the material which collapses in a black hole? And Stephen was originally arguing that this gets lost. Now, this violates one of the fundamental things about quantum mechanics, what's called unitarity, which suggests that information shouldn't be lost. But then I never really believed in unitarity at this sort of level anyway, because I think there's something wrong with quantum mechanics for big objects. So I'm quite happy for it to get lost. But anyway, this is one of these arguments. In fact, Stephen actually changed his mind later on at the Dublin conference and seemed to be arguing that it does get lost. But I'm afraid I'm going to have to say it's absolutely crucial, not just to this scheme. It seems to me when you think about it, it's actually rather important for more or less any scheme. But let me restrict my attention to this scheme. So it's because the information, this is a space-time diagram of a black hole which evaporates, don't worry too much about it. The point is that, at least according to the original argument that Stephen gave, it did depend on the information getting lost in the black holes. So I'm going to say it does get lost, and it's crucial, because this is where all the phase-space volume has gone. Now you might say, what's that got to do with here? I mean, suppose we sit in this room here, and the black hole's over there, a long, long way away, and who cares if that black hole suddenly goes pop? Well, we care, because how do you measure the volume in the original argument which I had here? You see, you have to take into account all the particles, all the things that are going on in the whole universe. And that involves the degrees of freedom in that black hole many, many light years away, which has suddenly gone pop. And I've indicated this diagram here. Those degrees of freedom, which are lost in the black hole, are going this way, and all the other ones that we might be interested in are going this way. And the point is that even though the phase-space volume doesn't get reduced unless the black hole disappears, and when it does disappear, it's because that volume, you see, is made up of lots of degrees of freedom you're not interested in, and those are in the black hole. So that volume can suddenly get reduced when that black hole goes away, but you don't notice it here because you're not using them in your calculation. It's a slightly subtle thing, and it took me a while to appreciate that's what's going on. It's just does this picture involve the black hole degrees of freedom or not? If it does, then you have to draw another piece out the back, which includes these other degrees of freedom, which I'm trying to express in this diagram here. Okay, well, that's as I say, it's a crucial picture to the whole problem, and it does require, information is lost in black holes, and it's crucially that which gives you the resetting of the effective phase-space volume in the next eon as being far, far lower than the one that we have now. And that is a consistency check, if you like, for the whole scheme. You have to make sure there is enough lost in black hole evaporation to make this work. And that's a calculation which I haven't been able to do as yet. So there are lots of tests of this scheme, even if we don't know yet about the ripples and so on. Which way has that gone? I have to go and study those emails, and there are lots of attachments, and I have to look at them all and see what they're telling me. So I'm afraid at the moment I can't give you any answer to that question. But even apart from that, there are many, many consistency tests which would rule this thing out or confirm it, depending upon which way they go. So thank you very much.